in on this. And I don't know who's actually watching right now, if anybody is. But I figured I'll get started. Originally, I thought I was supposed to be introduced by Don Blair, but don't know how that's going. Anyway, I'm Pete Marchetto, and I'm going to be talking to you about calibration and instrument building in citizen science. And this should be a relatively quick thing. Any of you who are on the Google event page, you should be able to actually come into the live chat on video or whatever, and let me know if there's any questions along the way. Also, I'll be keeping an eye on the Open Hour IRC chat on the actual publiclab.org page on publiclab.org/openhour. So, I've got Stevie saying hi, Pete. So I guess somebody must be watching out there. Hello. All right. Let me move over to my presentation. All right. Just double checking that everybody can actually see this. And somebody respond either on the chat or on the IRC chat if you can see the presentation. Well, I'll assume that's visible. So what I'm really into is creating new instrumentation. I actually do a lot of that. Just right now, for example, I'm working on a number of things. Stream gauging stations here in the Cornell Soil and Water Lab. And also, I'm working on a revamp of a rain machine here at Cornell. Some of the other things, I'm working with a couple of folks, or I will be working hopefully with a couple of folks out at the University of Minnesota soon on putting geolocator tags on the backs of penguins. We'll see how that goes. And so my background's originally in physics, but nowadays I'm doing engineering in the service of biologists, creating instrumentation for people who don't necessarily have the training to make it for themselves. All right, so that's my background. I just got my PhD in May here at Cornell, and I'm doing a postdoc with the Soil and Water Lab here. Let's see if, there we go. So I'm going to give you a brief overview of a couple of different things. Definitions for calibration, physical quantities that are used, standards and traceability, and drift. And then I also want to go into, actually, we'll probably be leaving drift for later. Then I want to go through a little bit about instrument building itself, some definitions used in instrument building, an overview of sensors, then sensing and logging. There is a difference between a sensor and something that does sensing, and we'll get into that in a little bit. Community builds, which are a big thing now in some of the open hardware circles. Hackathons and such have been going on for years in software, but this is one of the first, right now is a moment in time where we're starting to see hardware hackathons really come in with open source hardware for sensing and instrumentation. So then calibration of systems, and this is also where I want to make certain that you understand how exactly academia and government agencies can support citizen and community science. And then finally, data output, where I'll give you an example of one of the devices that we've already tested out here at Cornell that we're actually doing a community build on 4 o'clock today. I'm getting together with a 4-H club locally called the 4H2O group that's building one of these sensing stations. All right, so moving right along. Calibration. Here we get into the definitions. So everybody seems to think that calibration is something that's just done, or sometimes it has the appearance of somebody like waving a magic wand and saying, boom, you're calibrated. I'm here to tell you that calibration involves a two-step process that's repeated over and over and over again. You can only trust the calibration of a device for so long. And the calibration itself is broken down into two parts. Characterization, where you see how something works, and then adjustment, where you modify it. But then you have to go back to characterize it again and make certain that it's actually working. And then you adjust it again if you need to, and then you characterize it again, and then you get the idea. Another thing we're going to be talking about is DUTs, or DUTs, devices under test, things that are actually being calibrated or characterized. A standard, then, is something else we'll be talking about, along with uncertainty. Failure is just what happens when you've made an adjustment and you recharacterize and you find that you have to adjust again. Tolerance is something that's usually set using a Gaussian distribution, a bell curve, where you have an upper and a lower limit of what you're able to tolerate insofar as error, and that's related to your uncertainty. Certification or verification is the characterization we mentioned before, but being done with some sort of legal backing to the actual instrumentation that the characterization is done with, i.e., you have that instrumentation with, let's say that you're doing a calibration of a pH meter, and you've got standards that you've bought from like Sigma Aldrich or Cole Parmer or wherever, and those have come with a certificate of calibration saying that they have verified those standards to be within such and such an uncertainty of like 7 pH and 9 pH and 3 pH or whatever your standards are at. Those are verified and certified. Verification is is just checking it against a known standard. Certification is actually then making a legal document that says that the characterization has occurred against a known standard, and, well, we'll get into that a little bit later. Data, I think you all know what that is. Data are measurements, and we don't actually get measurements from sensors. Contrary to popular belief, a sensor is a transducer. It's something that moves information from one realm into another, meaning that you have energy of some sort, whether it be electrical energy, and you're trying to measure power across a resistor. Well, then the resistor is your sensor. Or let's say that you're trying to measure weight. You have a weight transducer in the form of a load cell or a strain gauge. And all of the signal processing circuitry, the measurement circuitry, all of that stuff that's downstream from that, that's not actually the sensor. The sensor is the thing that's actually doing the transduction. The rest is the measurement side. That's the instrument or the sensing system. And this is a very key difference that a lot of people seem to just completely miss. I've had people call entire SOND-type water monitoring systems sensors. And it's like, no, there are about 6 parameters being sensed, each by a separate sensor on this sensing system. Big difference. Sorry, a little bit of a pet peeve. A set point, then, is a known point that you're actually going to be measuring. And a measurement itself is an interpretation of a signal that you get from a sensor. Finally, a test accuracy ratio is basically a ratio of uncertainties between the standard and the device under test. And to give you a better idea, so definition-wise, this circuit in our top left corner here has a standard meter and a device under test meter. Both of these are measuring voltage at this point, and the device under test has some sort of adjustment, in this case, a variable resistor. And you're just measuring the voltage across a battery with leads that are about the same length, which means that you should have 2 different meters that are showing the same sort of output. Now, on the bottom center, you see a pair of graphs here. You see this Gaussian curve, this large, shallow one, and then you see this thinner, taller one. The taller one is that of the standard, which is usually going to have a higher accuracy and precision to it, whereas the shorter, more spread out one is usually the device under test. If you're doing your testing right, then you should have a more accurate device as your standard, the thing that's already been calibrated by somebody else, and which is instilling traceable calibration, we'll get to that in a moment, into the device under test. So this is just a comparison of populations of measurements given some input voltage and the number that you're actually getting. So if you take 1 million measurements on the standard and 1 million measurements on the DUT, or even if you take 10 on each, you're going to see this sort of curve develop on the higher uncertainty, lower precision device, the cheaper one usually, and this sort of curve develop on the higher precision device. The other thing that you'll see is a linear output, hopefully, where if you're measuring the V in by way of the standard, then the V out is from the device under test. And you should see a line like this, X equals Y, your V in equals your V out. The unfortunate thing is that in most cases, this is actually tapered a little bit at the bottom, comes up to a linear range, and then tapers off again at the top in what's known as a Y-bowl distribution. Once again, we'll get to that a little bit later. All right, so physical quantities that we can measure. Volts, current in I, or in amps. R is resistance, and P is power in this case. Then we have temporal physical quantities, that is to say frequency and time, and frequency is just 1 over time. And then we have spatial, that's actually an L, even though it looks a little bit like an I there. L is just length, A is area, and V is volume. So those three are also measurable. And then force and mass are also measurable, especially if you know what gravity is, then force and mass are roughly equivalent, hence why we use weight to measure mass. Fundamental measurements that we can actually make, though, when it comes to traceable standards and things of that nature, we can measure current in amps, we can measure time in seconds, distance we can measure in meters, luminosity we can measure in candelas, mass we can measure in kilograms, temperature we can measure in Kelvin, and quantity we can measure either by unitary counting, basically ordination, 1, 2, 5, 3, sir, etc. Or we can measure larger quantities in moles. So that's actually not something we normally have to worry about, because you don't normally have to worry about measuring that without using mass. Now, standards and traceability. Let's say that we have a worldwide set of standards. Oh, wait, we do. Those are at the BIPM, which is just outside of Paris, France. And that traceability that I'm talking about is that the various national physical labs, like Britain's National Physical Laboratory, the US's NIST, National Institute for Standards and Technology, the Canadian NRC, CNRC, German DIN, DIN, etc. All of these guys send their primary standards back to BIPM every once in a while to have them calibrated. Now, these guys do a lot of calibration work themselves for primary manufacturers of instrumentation, like, say, Fluke, Omega, what used to be HP and used to be Agilent and is now, I think, Keysight. On the electronic side, it's just Agilent on the biochemical side. And then there are also primary calibration labs, like, for example, there's, I think it's Spectrum Technology in central Pennsylvania, and up north of where I am, we have CalSource, I think it is, up in Syracuse. Those guys get their stuff calibrated either by going back to the primary manufacturers or actually going up to the national level itself for some of their standards. Then we have secondary manufacturers. This is these are people like BK Precision on the electronics side, or YSI, for example, if you've ever heard of them on the environmental monitoring side. Then you have secondary calibration labs. I used to work for one of those down in Pennsylvania. These guys use primary calibration labs to calibrate their stuff, and then in both of these cases, secondary manufacturers and distributors for those manufacturers will then send out via their distribution network. Like, for example, VWR does lab equipment, and they sometimes have calibrations done on site for them, and then they send those calibrated items out with a certification or a traceable calibration certificate. And secondary cal labs will actually come to you and do calibrations. Anyway, eventually you get up the tree all the way into the lab equipment that you or I would use. And on the citizen or community science side, you get into the situation where you now need to have people calibrate their stuff, or else, well, it's not necessarily going to be giving you values that will be useful. Finally, we are going to get into drift a little bit. How exactly shifts in calibration can occur? The causes that you can see, temperature causes drift. One of the papers that I have out is on how at Cornell Lab of Ornithology in the Bioacoustics Research Program, we had a whole bunch of recorders that were sitting under the ocean for a very long time. And at the end of each deployment, we'd wind up with a large number of different time constants. Basically, we'd wind up with all these shifts in timing, and it turned out that the clocks that we had that were dictating how quickly everything was sampling were shifting with respect to temperature. Gravity can cause drift as well. If you have a little resistor, a variable resistor, for example, that has a pendulum-type wiper in it that will move, if that's bapped around enough, that will eventually start moving towards its lowest potential position, which means it goes down. And when that goes down, then that shifts some gain function or something else inside. And finally, aging is another issue. Electronics are, despite their silicon composition and otherwise resemblance to rock, they're not necessarily rock solid insofar as how they change over time. The behaviors that change are the gain function itself, meaning if you go back to that other figure that I showed before, this down here, V in versus V out, that's the gain function. So the gain function itself can start behaving differently. It can be not aligned sometimes. And then the offset on that, where it meets the y-axis, that can also change. So now we're going to get into instrument building, but first I just wanted to back up for a moment to the open hour chat room and also the just the group chat on the Hangout here, and just open it up for any questions that we had about calibration and characterization. Anybody got any questions before I go on? All right, I got nothing, so we will continue on. All right, so as I said before, a sensor is essentially a transducer. It's something that allows you to change a physical quantity of some sort into usually a voltage or maybe a current or a resistance. It makes it so that you're able to take some sort of physical quantity and turn it into an electrical signal. Now, a sensing system or an instrument is the thing that will then record that signal and or turn it into another physical quantity that can then be measured. So, for example, if I've got a if I have a proximity detector like the one that I use in the depth gauge you'll see in a moment, that's going to that's a sensor that turns distance into voltage. And then if I know how the gain function on that works with respect to voltage out from the sensor versus number of meters of height, then that will allow me to actually get a measurement out of that in meters. Now that signal, as we were talking about before, is just a voltage that changes with respect to time, and the sensitivity is the actual characterized number from the sensor and the sensing system all through that gives you how many, in this case, meters per volt we've got. Or if you're doing acoustic work, for example, then it's volt. It can be either pascals per volt or volts per pascal, depending on which way you like to convert it. So now, moving over here, some pictures finally. We have those depth gauges I was talking about on the left here. Those are both just PVC pipes, spray painted black on the inside with an infrared distance sensor up in the top cap. And the sensor has 3 different wires going to it, one for positive voltage, one for negative voltage, and then one that is just the signal coming back out. And so we've used this both in the lab and also in the field, and we've characterized the gain function of it so that we can actually figure out what the full sensitivity is, how many volts per meter or meters per volt. And then in the middle, we've got another design that I've been working on that has 2 Hall effect sensors. Both are magnetic field sensors. It's based on the idea that dissolved oxygen modifies the magnetic field in water. So we've got 2 magnetic field sensors with a magnet in the middle between them. And then, as you can see in the diagram behind it, there's a gap between one of those and the other. And then the other one has just a piece of plastic or something else that's paramagnetic rather than ferromagnetic, sitting between that sensor and one side of the magnet. So we're able to measure what the difference is between those 2 Hall effect sensors' signals, and that should be proportional to the amount of dissolved oxygen moving through that flow gap. On the top right, you can see a rather abused looking, by way of hot glue, both pH meter and moisture meter, or sensor for both, that we recovered from one of those cheapo, like $10 moisture/pH sensors that you can just put in the ground with your plants. And it actually works to a certain extent. I mean, I'm not going to say that this is going to replace something that you got from Cole Parmer that you've got in your lab, but for massively deploying this amongst a bunch of citizen science groups, for $10, you can't do much better than that. And then on the bottom right, you've got a demonstration of an ultrasonic depth sensor that I've got over a hole in the ice where USGS is gauging on 6 Mile Creek over here in Ithaca. And I was just looking to see how that worked for actually determining water depth. All right, so sensing and logging. We do this with a data logger. And in this case, we've got 2 pictures of the same type of data logger, which we use in the Soil and Water Lab. This is one that I designed. It's based around the Arduino microcontroller. And we're upgrading these soon to the Wicked Device Wildfire microcontroller board instead, which is based on the Arduino, but which has Wi-Fi capabilities, and right on board has the capability of taking a micro SD card that we can log data to directly. So we can also transmit data back as long as we've got a Wi-Fi signal. These pictures are from a community build that went on at the Homestead Montessori School in Glen Spey, New York this past August. We've got a few people here who are from various different organizations. The guys in the top right picture, for example, are from Water Defense. The guy on the bottom right is from the Susquehanna River Basin Commission. Then we've got, in the left photos, we've got one person from the AmeriCorps Watershed Ambassador Program, and oh wait, there's Don Blair there. Hi, Don. And a couple of teachers from the school itself. And what we were doing here was actually building gauging systems over the course of 3 days and making these ready to go. The only thing I had to do was send software to these folks. Now, unfortunately, we don't have most of these folks with their gauges online yet, just because of the fact that we need to get them to install the software or the firmware onto their wildfire boards. But once we have that, we'll have, I think that's going to be 5 or 6 different gauging stations. They'll be up online and able to give us back measurements of turbidity, conductivity, temperature, and depth all at the same time. All right, so calibration of systems. I was mentioning before how most devices actually follow this curve where you have this linear region in the middle. This is the Weibull distribution. And then you have these logarithmic and exponential tapers on either side. Well, it turns out that most devices are only linear for a short period. And some, like this blue or red curve, those would be less sensitive because their linear region is very short relative to this big long one on the yellow line here. And so that's what we try and optimize for when we're picking a sensor. Now, the other thing is that once you have that, where X in this case is our input and Y is our output, meaning this on the depth gauge, for example, will be in meters, and this, our output, will be, let's say, in volts. Ignore the numbers, they're not actually useful except for as coefficients to the maximum voltage. Then we can do the characterization based on this curve. So after we build the sensor, we characterize it, and then from the characterization, we get a sensitivity number. From there, we also do a characterization of the whole system that it's attached to. So in this case, we've got a SparkFun Red board that's taking data from this system by actually recording the signal, or actually outputting the signal from our depth gauge's proximity sensor out to my laptop. So then, after we've characterized the system all the way through from the sensor into the thing that's going to be doing the analog to digital conversion, where we actually go from a voltage to a number, then we're able to create what's known as the transfer function. This is very similar to the gain function, except for the fact that the gain function or the sensitivity both stop at the sensor, whereas this actually gives you the sensor and what it's hooked up to, the rest of the measurement or sensing system. After that, we go through sensor or system use after we do the adjustment side of things, in this case just adjusting using math, and then we get data output. And the data output that we see here is for one of those 4-parameter stream gauging stations that we had put out. This was during an ice melt event on Cascadilla Creek just south of campus here. Here at Cornell, and you can see that the temperature is trending upwards. Well, this is why we know that it's an ice melt event. The temperature was coming up. By the way, you notice that there's no actual useful units on the left side, but we can actually calibrate after the fact and figure out what these values, which are in least significant bits initially, come out to in physical quantities later. So that's another thing, is that we're able to save energy by not doing the calculations right on board. We're able to instead save that for later, use the sensitivity that we've calibrated either before, during, or after our deployment of the sensing system, and then actually get real numbers afterwards. So in this case, the temperature was trending upwards. The depth started to trend upwards as well. And what was interesting about that was that the depth was trending upwards at most the first derivative of the temperature. And the cool thing about that is that's the way it should be. If temperature's rising exponentially, for example, then the depth should be rising linearly. Or sorry, if the temperature is rising quadratically or cubically, then the depth should be rising roughly linearly, because the depth is related to the flow rate overall, including the cross-sectional area and the height, whereas the temperature is just giving you what the potential is of the ice pack to essentially dissolve and melt away into water. Now, the other cool thing is that as we've got more volume of fresh water coming out of the ice, you can see that both the conductivity and the turbidity are trending downwards, which is also spot on, because the turbidity, anything that's in the water that's making it turbid, is going to wind up being diluted, whereas the conductivity, that's also a dilution thing where the salts are going to be diluted. And oddly enough, both of these seem to be decreasing at almost exactly the same rate. which is inversely proportional to the temperature. So with that, I leave you with an uncalibrated data output from one of the systems that we've built, and ask if there are any questions. You can ask them either on the group chat right here on the Google Hangout, or you can actually ask them on the public lab down here. And Stevie on the public lab IRC chat is telling me that if I click a button from the top of my Hangout, I can get a link for people to join in the call. Let me do that right now. I'll stop the presentation. Hello again. And grab that link. All right. If the IRC thing likes me, there you go. And I'll also tweet this link just in case anybody doesn't have access to those other 2 points. I'm Petmar0 on Twitter. All right. Questions? Anyone? Answers? Answers to my call for questions. Let's see here. Well, one of the questions that I know I already have from Don is, what about instrumentation time? There's an irregular Google Hangout that I do with several of my friends who are also in the instrumentation biz, so to speak. Sorry, hold on a second here. Hello?
Hey, Pete, this is Don. Are you?
I'm still on.
Okay, it's really funny because we're seeing you with a bit of a delay. But it doesn't seem like it's possible for us to connect with you in an interactive way.
I just sent that link over. That didn't give it to you? Or that didn't...
Let's see. Maybe there is a link. It's really funny because we've got you broadcast like from 20 seconds ago, so it's really weird that we're talking to you in the future and then seeing you in the past.
Well, here's the updated link is on publiclab.org/openhour.
Okay, cool. Sorry for the technical difficulty. Your presentation was amazing.
I tried.
we all really loved it. So we're just, so maybe we can, we'll just try to quickly figure out now if we can do this interactively. So this is, the new link is?
Should be right on the Public Lab Open Hour page. And also, I just re-invited you again, which should be coming through. That should be that noise that I'm hearing right now.
Oh, gosh. Okay. Wow. Wait, oh, yeah. Can you send that again? Call again. Now I'll be able to answer.
Okay. Invitation posted. I have an Ellen who has just joined. Hello?
Hi.
All right.
Stevie, I was testing out your link.
Okay.
Sorry.
Sounds good. Okay.
Sorry about that.
No,
Yes.
no worries. Thanks for posting that link. It's Stevie. So I was just testing it out.
Okay, cool. Yeah, I'm hoping that Don and the rest of the folks will be on here momentarily.
Great.
Here's
Thanks for your presentation. It was really interesting.
Glad you liked it.
Yeah.
It's an interesting subfield because there's not many of us around, it seems, doing instrumentation for ecologists, environmentalists, biologists, etc. So
yeah.
I'm just one man with a background in physics. So we'll see what other questions wind up coming up, if any. Supposedly the other folks have joined? No?
I'm getting people who are now on the public lab chat too, so I'm just sharing out your link again. So
okay.
They should be joining any minute.
Thanks.
Mm-hmm.
There's always a hiccup of some sort whenever I use Google Hangouts.
Yeah, they can be tricky. I know. I've been doing a lot of them over the last year, and I still get hung up on it sometimes. But it does seem like one of the better formats for sharing with a lot of people.
So maybe they should call it Google Hangups rather than Hangouts.
Smart.
So may I ask what your affiliation is, or if you're involved with Public Lab? Or
Sure, yeah. I work with Public Lab as Outreach Manager.
Okay, cool.
Oh.
There is a Patrick who just joined.
Hi, Pat.
Oh, so am I joined? Pete, thank you very much for the call.
No problem. And I think I see Don.
Yay! We made it! We made it.
Somehow.
Sorry about that. Okay.
By the way, may I ask why demand equals 1 person equals 1 cubic meter? So according to the wall behind Don.
Oh gosh. Oh, sorry. That's not our doing. That's nefarious MIT people. So sorry to interrupt, but after you should keep going. But then at some point we can introduce the people that are sitting around the table here. We're just very happy to be here. I feel like we're all collectively like Matt Damon, and we just got rescued. This is great.
You know how much the U.S. has spent in various different movies to bring Matt Damon back? That's been a thing that's been trending online for a couple of weeks now, between The Martian and everything else. Come on.
He's worth it. He's worth every penny. So hey Pat,
intros. Go ahead.
Yeah. Hi, you guys.
Sorry, you folks were talking about something, and then we can go around and introduce who's here later if you want.
Are you talking about us folks online?
Yeah, you.
We're just kind of introducing ourselves to each other anyway.
Oh, okay. Cool. Well, then, okay. So this is Dave. Hey. Sam. I don't want to say anything.
From Civic Media.
Sans from Civic Media. Joe. Hello. I'm Joe. Emily.
Hi, also from Civic Media.
And then this is awkward, but we're watching you on 2 screens like that. So anyway, and then I'm Don. Great presentation. That was amazing. Sorry that it wasn't so interactive until now, but maybe this works out fine.
As long as there are questions, we can be as interactive as we want it to be. Just kind of introducing ourselves to each other anyway.
Okay. Oh gosh, we have a delay as well. But anyway, okay. Well, so I mean, one thing that occurred to me was, I mean, that seemed like a really nice characterization of the entire chain of calibration. You had a really nice slide that had all of those boxes on the bottom showing from like the sensor all the way to data out on the other end. And I guess I was starting to wonder, so if I want to, for various applications like that might look different.
Hi,
so
Jeff.
Oh, Jeff is here.
Hello, Jeff.
Jeff is muted.
And Don, I think this is the slide you meant. Is that it?
No, it was one that was further into the presentation, and it just had boxes along the bottom.
Oh, I'm sorry. Yeah, I know which one you mean. There we are. That one?
Yeah, exactly. So if I'm just trying to imagine, like I'm someone who, say, is worried that I have a rainwater catchment system in my backyard, and I'm worried that something, a squirrel might have died and started rotting in the tank there.
The first sensor that you need to use is your nose.
Yes, but I think that's actually a great point. That there's a way in which, depending on the audience and the project, that might be enough. I mean, I smell rotten squirrel, and that's enough for me to go to the next step. So there's a way in which this diagram, it's almost like an ideal process for certain projects, but it's maybe overkill for, depending on the question. Sorry, that's a vague way of putting it. But
I understand what you mean, and the thing is that I would say that it's not that it's necessarily overkill. It's that, as you said, it's an ideal system, and parts of this should be taken up by different people. Insofar, the 5-step model that we've been working on here at Cornell is that step 1 involves having people actually build the system, or having us design the system. Step 2 is that people actually go ahead and build the system who have an interest in deploying it. Step 3 is that they actually send it back to us, and then we do the calibration and characterization and adjustment and all that stuff. And then step 4 is we give it back to them and they deploy it. And then step 5 is 5A and 5B. 5A is that we bring those people back together again, all of these different groups, to then hash out, okay, what went right and what went wrong over the last year's calibration cycle. And step 5B is that after the course of a year, all of the sensing system comes back to us for recalibration so that we can actually make certain that our citizen or community science data is actually as reliable as something that you get out of a lab or out of a USGS gauging station, for example. So by distributing the responsibility for different parts of this among different organizations where those competencies lie, you can get the entire chain of characterization that you're referring to at the bottom of that slide without having to sacrifice loads of money or loads of time. Because at Cornell, we're right now in the midst of building up a calibration lab specifically for community science instruments that will also be used for the rest of the university, whoever wants to use it. But the primary goal is that we get stuff in from community science groups and we calibrate it for them, have a NIST traceable certain actual calibration certificate, which functions as a legal document. And as you were pointing out in your initial description, Don, that then confers this magical trait of traceability onto that device, meaning that anything that you get from that device is then, in certain legal senses, for example, actionable. If you have something that doesn't meet with EPA requirements, for example, if you have so much BPA that's in your water supply, or so much phosphate or nitrate that something that is supposed to be drunk or drank is undrinkable, then as long as you have that verification, then that's something that you can actually do something about legally. So by distributing that responsibility back onto academia, where we can afford it, from the community science groups who can't, and making this freely available to them, then we give a whole new realm of precision to what would otherwise be considered just community science instrumentation by a lot of scientists.
We might, okay, I think we got that last bit. We froze for a second there. Are you hearing us?
Diatribe. You didn't miss much.
Oh no, that was fantastic. And I want to let other people jump in with questions. But I guess one thing that occurred to me is, so I really like your description of the way in which we can distribute different parts of that chain, and so it's not so onerous for any one individual or
Organization.
Yeah, or organization. And I like the idea of thinking about how various parts of that chain could be taken up by various entities. So even when we're talking about calibration, what are the possibilities for, say, a community developing their local expertise in using instrumentation that they have in that community center to do enough calibration and such that they're able to get the answers to the questions that they have. And you're right to I like the way you're describing this kind of like magical special sauce that certain sorts of validation seem to require in order to be blessed by certain agencies, and the legal system. But I guess, and that seems like a difficult thing to engage with. I mean, very, very exciting to engage with, but
Not
there's
as difficult as you think.
Yeah,
because if I were to get just a multimeter calibrate, that would probably be about $20, and I'd have a legal calibration certificate that said, yes, 1 volt here is equal to 1 volt plus or minus 0.001 volts according to NIST in Gaithersburg, Maryland, which is in turn according to BIPM in France. So it's not difficult to engage with. That being said, you do have to find a good calibration company nearby, but those people exist. And there are services like A2LA and EMC3, I think it is, that all exist. And mainly the American Society for Quality is another organization that you should be aware of. ASQ especially has a record of all of the member organizations, which are mainly second order or citation labs, like I was talking about before, and they're pretty cheap. So I mean, if you have a makerspace nearby and that makerspace wants to get their oscilloscope and their multimeter calibrated, guess what? You actually are able to confer traceability even from within that. It's not like you need to be specially trained to say, oh, here's the stamp of approval. It's not like being a notary, for example. Although it does have other resemblances to the notary system. But yeah, by and large, if you're trying to make certain that you have a physical measurement that is well characterized and that you've conferred the proper traceability, it's better to go with some means that's essentially commercial. That being said, if you're only interested in the answer to your question for your own reasons, like for example, if you're looking at thermal plume formation in a local stream, or say the Gowanus Canal, and you want to get a confirmation that your thermal sensors are working, that you can do by physical standards. If, for example, I take a beaker, I put ice in it, I put acetone, I put isopropanol, and I put water. Now, until the ice melts, all of that's going to be at 0 degrees C. So if I put the temperature sensor in there, then whatever it reads should be equivalent. Whatever it reads voltage-wise or numerically, if you're going through an analog to digital converter, whatever that is, that's going to be equivalent to 0 degrees C. Now, as we heat the beaker up, ice melts, we start seeing an increase in temperature. Then we'll level off again. As we keep heating it, let's see, I think acetone's boiling point comes first. I think that's 56 degrees C. So we'll start seeing that a log of the sensor output will flatten off, and we'll know that that's exactly the boiling point of acetone. Thermodynamically, it has to be. So if we get that little shelf, that mesa, or that flat spot, after we meet the first inflection point, now we've got a thermodynamic means of saying, okay, now we have 2 points of calibration. All of the acetone boils off. Now our apartment smells entirely like nail polish remover, and we move into the isopropanol phase. And that once again, you get up to the boiling point and then it flattens back out. And you'll see, once again, that right at the middle of that boiling point, you know exactly what that temperature is, because at 1 bar, at 1 atmosphere, the alcohol will only boil at 1 temperature, and it will stay at that temperature until all of it is boiled off. It's just like the basis for the distillation process. And finally, you get to water boiling. So that's at 100 degrees C. You now have 4 points across the range of 0 to 100 degrees C that you can use to definitively say, at these different points, due to a physical standard, I know what the temperature actually is and what the actual output from my temperature sensor is, and what the output from my sensing system or data logger is. So by doing it that way, you have a physical standard which, while not technically traceable, will still allow you to answer questions with known quantities. So it may not be blessed, as you put it, with traceability, but it is still a good way, or it's even a, I would say, a best practice to allow you to say definitively worth considering to continue our work on. Then you get into calibration, but if you're just looking for whether or not there's a large enough thermal shift that it's worth it, there are other ways of doing it.
That's fantastic, and it sounds like some of those methods might be more than like every individual would want to do. So that's where you would.
Well, yeah, I mean, not unless you want your apartment smelling like nail polish. Remember?
Right. Exactly. But you'd want some. You'd want a community center or something where people would have. So I'm just imagining what are these structures that are not a university lab, are not like something like that, but more like, in a neighborhood, there's somebody who says, yeah, I don't mind my basement smelling horrible, so I'll take care of the chemicals, and I've also, spent enough time with this process that I've gotten pretty good at it, and then they're kind of trusted in the community to do that sort of thing. I'm interested in thinking about like what that looks like.
Yeah. Just to follow up, if I might, to Don's question. This is Pat Coyle. Don's getting ready to travel to Colombia and deploy a number of the riffle type water sensors. And I think about in settings like the developing world, where there might be a variety of information that you'd like to be able to monitor and report on, and find ways to have adequate confidence in the results, that in these communities that people have a useful tool. The one example you mentioned in this case, where you can get physical properties by the way that the mixture of solution going from ice to the first boiling point to the next boiling point and so forth allow you to do that. I'm very interested in sort of the ways in which we can have people taking measurements that can be helpful for them in terms of the benefit to their community, whether it's pollution in their water supply or other kinds of important to their well-being and health kind of circumstances, not necessarily where they need to take intervention action where the results may be challenged by adversarial people questioning the reliability or the accuracy or the calibration of their instruments. But in that context, it seems interesting to me to think about ways to use these very lightweight and increasingly ubiquitous tools for being able to make measurements and display them and communicate them together.
Well,
Thanks.
if I remember correctly, Don, the riffle is temperature, conductivity, and what else?
At this point, it's temperature and conductivity, but we're looking to do turbidity soon, and because it works like an Arduino, we could imagine hooking lots of different sensors to it.
Yeah, I mean, some of the stuff that I've done could even be used with that, like the depth gauge, for example, which I think we've talked about back in August. But to get to your point, yeah, for example, with conductivity, you can buy, along with the rest of the components that you need for the riffle, you can also buy 1% resistors that come with a certificate that says, oh, well, this is plus or minus 1% from so many ohms. So if you have 3 or 4 of those at different values and you just put them across the 2 electrodes, now you have a way of saying, okay, well, this is the amount of conductivity in Siemens or the resistance in ohms that we have, and this is the signal that we get out from that. So that's a way of characterizing that sensor. And then on the other side of it, if we were to look at turbidity, for example, reading of a Secchi disk is still more of an art than a science, as it were. And so calculating number of NTUs that you get out, we're working on that with different displacements between white LED and a photoresistor in our case. You can do the same thing with a phototransistor. You can do it with different color LEDs. But really what it comes down to is that we've got a light source and then some sort of receiving sensor that's giving us how much light is getting through the water. And so mapping that to number of NTUs could be easy from two different perspectives. Either A, you buy the actual calibration vials, which they're a bit expensive, and you want to keep them sealed because despite being developed by the EPA, there are loads of really nasty toxic things in those standards, which there need to be in order to keep the tiny little microbeads and such that are in there suspended in solution, or rather just suspended in an emulsified mixture so that you can get the same reading day after day after day from the same vial. But the other thing that I found is that you can also do the same thing with a Secchi disc, a miniature one that you make out of paper and meringue powder. I mean, you do the same thing where you just stir that into water, or actually another one that I've found that's an even better emulsion, chocolate milk and water. Use that with the miniature Secchi disc. You do your calibration by first figuring out what the number is relative to what an actual Secchi disc in a stream or a lake would look like. And yeah, Don, diluted chocolate milk absolutely sucks taste-wise, I gotta tell you. There was one kid in 4H2O who decided that he was going to finish off all of the samples. Spit it out after like a minute. It was like, oh man, this is nasty! But yeah, chocolate milk actually works really well because milk is an emulsion in and of itself, and diluted milk stays emulsified down to a critical point where eventually it starts settling. But the micelle weight is low enough, especially in cow's milk and cow's milk chocolate milk, that it will stay in suspension for a good long while, certainly long enough for you to get your measurements. So that's just another way of kind of auto-standardizing, if you will.
Thanks. That's good tips, good points.
Pat, if you have a follow-up, you should continue, but Dave here has a question after you.
No, I'm set. Thank you.
Okay.
Okay. Hi. Yeah, I had a question. So, I mean, these methods sound great, and I know there's a lot of different published sources for methods, but did you have...
I'm sorry, did I have what? I think Dave is frozen.
Yeah, they froze. You're frozen, people.
Dave, you're at 0 degrees C, which means we can use you as a standard.
Oh, there, you're back. You're back.
Oh, we're back. Yeah, so I don't know if you got that. We were just... So if you had a recommendation for like an open published set of calibration procedures?
Well, there is an open published set that's actually from the U.S. government, but you have to jump through a couple of hoops in order to get access to it. So open is with quotes around it. Through a service known as GUIDEP, the Government Industry Data Exchange Program. And so they allow not-for-profits who provide any sort of information or data or product to the U.S. government to access calibration procedures for any number of different electronics or mechanical instruments, and even just broad protocols for whole classes of instrument that have been developed by naval aviation electronics technicians and also the Air Force's electronics folks. So that's one place that you can get those. Another place that you can find some of the protocols that I myself have written, although I'm by no means the expert in this. I'll put a link up in the chat there, but we have a, actually, Don can tell you a little bit more about it, I think. We've got the, we have this page on GitHub for the stream gauging sensors that I've been working on. And let me see, bring this up quickly, because what we actually have is, yeah, here we go. This gives you, at least for the 4 parameter that I was talking about with, yeah, here's the link. github.com/slowwaterlab/streamgauge, and then if you click on cal.md, you'll see there's a pre-cal procedure and then characterization for the depth sensor. Then we also have the temperature characterization and calibration, the conductivity characterization and calibration, and finally the turbidity, which the turbidity one I'm going to need to change because that was done a couple of months ago before I came up with the idea of using chocolate milk. So I think that's going to be changed over to chocolate milk soon.
That's great. Thanks.
No problem. And that's the other thing, is that between where I am right now as a postdoctoral research associate and as of January I'll be an assistant professor at the University of Minnesota. So in both capacities, I'm still writing these protocols. So if you need one, contact me.
Oh, that's great. You'll do it on demand, huh?
Yep, because the nice thing about protocols is that they're also known as methods papers.
Ah, okay. It all works out.
Yeah, exactly. I get my academic coin of the realm, you get a nice calibration procedure, we're all winners here.
Uh-huh. Jeff, Stevie, any questions?
Okay, I'm still on that call too, but I had a bathroom break with a bit of a breath.
Oh. Let's see. They both. Oh.
There's Stevie.
Yeah. Stevie, do you have any questions or anything from your end, or I don't know if Jeff does, but and like Patrick is gone. Everybody's gone.
Where did everybody go?
I have to jump off as well, unfortunately. But I really appreciate you sharing the presentation, and I'm hoping that you're okay if we leave it up on Public Lab so that people can come back and watch it who weren't able to join us today.
I'd love for that.
Great.
Cool.
But, yeah, thank you, and I apologize for needing to leave now.
Oh,
but,
no.
Not a problem.
Glad this could happen, and yeah, anytime that this space can be used to share out on ideas or questions or things like that, it's good.
Cool.
Alrighty.
Thanks a lot. Nice meeting you.
Great. Thanks, Stevie.
Anybody else around the table there with you, Don?
I'm gonna just go around the table, and we're just gonna like do that thing where you say like, "What's your question?" Okay, Sans, what's your question?
My question is, I was wondering if you could say a little bit more about the difference between testing the sensor versus testing the entire system. Is it just that you're reading it at a different point after the ADC, or like what is really different there?
So the thing is that the sensor itself has intrinsic physical properties, and so does the analog to digital converter and the rest of the signal chain. Starting out with the sensor, your signal chain is comprised of the sensor itself, then whatever means you have of amplifying that, which even if it's an amplifier of gain of 1, meaning a piece of wire, which then has its own properties. Basically, what I'm saying is that every component acts as a bandpass filter in the frequency realm. Every component acts as an attenuator in the DC voltage realm. So you need to account for every single component that goes all the way through when your signal becomes digitized. So the sensor is only the beginning of that. If you have a long run of cable, you're going to have resistive losses. So how your sensor behaves at the end of a long length of cable versus how it behaves if it's right on the same board as your analog to digital converter, two very different things. So if you have one scenario and then you change it to the other, then your characterization is as good as useless. So if, for example, you have a 20-meter lead to your depth gauge, and then you go directly into a wildfire board or an Arduino, into one of the analog to digital converter inputs, then that 20-meter length is going to give you some amount of resistive losses, and that will drop your voltage by some amount coming from the sensor. So then you need to characterize the sensor itself at the end of the 20-meter length, and then you have to characterize the ADCs, because that's the other side of this. If you've ever looked at how analog to digital converter voltages float, especially on multi-channel ADC, if you ground, say, channel 0 on an Arduino, and you're looking at channel 0 and channel 1, you'll see that channel 1 also drops in voltage because of the fact that it's capacitively coupled to channel 0. So you need to basically build the entire system as well as characterizing the sensor, and then look at what the characterizations of both are. Now you have essentially two parts to your transfer function. If you multiply those by one another, then your output is actually going to be proportional to the entirety of the system that you're working with. Does that make any bit of sense? Or?
Yeah, absolutely. That was really useful. Thank you.
No problem. The other comparison that I'd give you is, so I spent the last 6 years doing work in the audio realm, and one of the things that we always run into with audio is that you have two different uncertainties. One is frequency, the other one is amplitude. And so in the audio realm, it's even more important, because if you've got a microphone with some known frequency response, then you also have that Weibull distribution I was talking about before for the amplitude response. So now you've got three different axes. You have the frequency axis, you have the input amplitude axis, and then you have the output amplitude axis, which is your z-axis. And that's just for one element. That's just for the microphone. Then you have the bandpass and the amplifier, both of which have their own behaviors, and then you have the analog to digital converter with some uncertainty to its frequency. So if I'm talking about stream monitoring, way simpler than doing a characterization on a full signal chain for an audio device, but still just as important. So just wanted to give you a it could be worse scenario.
Amusingly, we're actually using microphones here. So,
Actually, yeah.
So thanks for that.
I was just going to say, if
just
Jeff,
so you know, the bioacoustics research program at Cornell has a fully calibrated bunch of instruments and a massively underutilized anechoic chamber that you could probably negotiate for a cheapest free usage of if you're interested.
No.
That's super cool. We actually have a couple of people around the table who are working on the beginnings of a sort of distributed citizen audio like amplitude characterization project that it would actually be great to get your feedback on. And maybe we could even do that now. But
it's a terrible pun, Don. Feedback on audio stuff? Come on, you're better than that. Sorry. I can definitely provide feedback on audio, and the other thing is that I'm not certain if you're aware of it, but there's a group down at NYU that's apparently doing a similar sort of project. Are you aware of that?
No, and we just lost everything you said from when we asked the question to now, so we caught the NYU.
Okay. Well, I was accusing Don of making a really terrible pun, so apparently Google Hangouts didn't like that.
I'm too dumb to understand the puns when I'm making them, but it's great that I make them, and then later.
The pun was that you were asking for feedback on.
Oh, okay. Oh, God.
But, there's a group at NYU that's doing something similar, where they're looking at ambient noise in New York City. Are you familiar with that at all?
No.
No, that's already huge. That's already great. Thank you.
No problem. I'm trying to remember the name of the group, but they've got like a satellite campus in Brooklyn, and they've got CS folks working on this sensing system that's essentially equivalent to a Raspberry Pi with two microphones on it. There's also the Robin system that was pioneered by the Cornell Lab of Ornithology, which I actually built the Generation 1 units of. And that was basically, once again, a USB microphone going into a going into a Raspberry Pi. Only thing is that with that, they weren't looking at amplitude, which also was a bit of an issue because there was an automatic gain controller on the microphone line. But they were actually looking at the signal itself to determine what, if any, birds were making making night flight calls while flying overhead. And the names you'd need to know for that one are Andrew Farnsworth and Matthew Robbins, 2 Bs. They've also been, well, Matt has been involved also in the real-time detection world in the AutoBuoy project, which has been going on for a few years now between bioacoustics here at Cornell and the and Hui, actually, where Hui sets these buoys out, and we've got Cornell has these audio detectors that are on them that are listening for North Atlantic right whale calls. But one way or another, yeah, both of these groups, both at NYU and also here at Cornell, might be very, very interested in collaborating with you on these topics for audio.
Super cool. Do you, I mean, if you want to describe the, or you don't feel like it now, maybe, but like, do you want to?
There's not a ton to describe right now, but we've just been playing around with a little microphone which does have gain control, which we're realizing is not the most effective tool for measuring ambient noise, and an Arduino and a little battery pack. But we've got it basically communicating with a mobile app that we had created to help citizens monitor infrastructure issues in their community. And so we can link via Bluetooth and just kind of upload a stream of data from the sensor and then ask them when we sense that they're in particularly noisy areas, when it crosses a certain threshold, ask the citizens to give some additional input, like take a picture of where you are or tell us what are the main sources of noise where you are. So we're playing with just kind of integrating that into an existing mobile app to get sensor data plus citizen contextualization of that data.
Okay. The other thing you might want to look at, though, is the I think it's just the soundboard by SparkFun. I mean, if you're buying the Arduino, I'm guessing you're probably buying it from them.
Yeah.
Or Adafruit.
Adafruit, I think, is where we got.
Okay. You might want to look into buying the soundboard from SparkFun, which, once again, I can send you a link to. I've actually characterized those in our anechoic chamber here up to, I can't remember whether it was 8K or 20K, but they were pretty much dead flat. And the nice thing is that they have an envelope follower pin. So instead of having to do the audio processing on your own, you can actually trust the device itself to just give you a DC level output proportional to the SPL into it.
That's helpful. That's just what I was going to talk about this afternoon.
The thing is that SPL measurement is an absolute pain, and you need to. The other thing is that you need to usually mimic the hearing curve that you're trying to get for that. So especially for humans, that means you have to build a hardware implementation of the A curve, and that is a pain and a half. Then on top of that, you have to characterize it to make certain that it's replicable across the population. That's, I think, why, if I remember correctly, we only went up to 8K on the soundboards. But let me get you the link to that. The other nice thing is that Pete Doctor out there is perfectly willing to part with a couple of those as samples if it's for a citizen or a community science project.
Okay.
And you can tell him I said so. Yeah, the SparkFun sound detector, 12642, and here's the link. Coming up right about now.
And how? So once those have been characterized in the way that you described, to what extent can you pretty much rely on the manufacturer producing them consistently enough that that characterization was good enough?
In most cases, you can't. I mean, especially in the case of like SparkFun's thing, there's an offset control on there for the comparator that allows you to also get a digital signal when you cross a threshold. But the thing is that the JFET that's inside of the Electret microphone gives you a different amount of current based on whether the LED that's tied to that is on or off, which means that setting that threshold actually changes the gain in the envelope detector and even in just the audio out pin. So you need to set all of those to be the same and then measure those with a comparison calibration or a comparison characterization where you have a known standard. Usually you'd buy like a $200 SPL meter from Newark.com with a calibration certificate, and then you just have a bunch of these sound detector boards that are sitting right next to it. You have them all lined up facing the exact same way, and then you just have the same stimulus sound playing out a speaker to all of them. As long as they're equidistant from that sound source, you should be able to do a side-by-side comparison and characterization with no problem.
Oh, great. Okay. So, okay, that's good to know.
Mass cal in one go.
Yep.
The problem is you can't source that sound to community users, so to speak, very easily. That being said, there is another way of doing it that we had investigated here, which is that piezo transducers are actually extremely repeatable even from the manufacturer. So if you have a piezo buzzer and you have like an LM7805, which definitely regulates to 5 volts plus or minus 10%, then that means that you should have the same amplitude plus or minus, I think we calculated it out to be like 5 to 7% on the SPL. Now, that being said, that's SPL, which is dB re 20 micropascals, and this is sensitivity, so it's dB re 20 micropascals per volt, and it gets really complicated when you're trying to figure out how far out you need to go in order to get from this logarithmic unit of dB re 20 micropascals, or dBSPL, or dBA, or whatever name for it you want to use, versus having the output from the voltage on all of these units. So that logarithmic offset gives you a weirdness to your percent uncertainty. That being said, single or double point calibrators are also not all that expensive. I think we bought our 2-point calibrator, which goes at 1 kilohertz at both 94 dB SPL and 114 dB SPL for about $150 with a CalCert off Newark.
So that's another example where maybe you have a community center or a maker space that has one of those things, and you in the local neighborhood, and you have people go to that place and get their devices calibrated.
Asterisk. The asterisk being, of course, that then needs to be set up on a regular returning calibration cycle, that it can be sent out for recal so that you're certain that it's still in the right range.
Wow. Okay.
Because aging ruins everything.
Aging
It really does.
If you take nothing else away from this talk. Yeah.
The way that you defeat the aging function for most of these things is you just have an annual calibration cycle. You have to send your instruments out to be recalibrated by another calibration lab every year. Yes, it is a racket. Yes, it is a pyramid scheme, but it's a useful one. There's a reason I inverted the traceability tree into a tree rather than being a pyramid of traceability, which is the usual way that you put it, because I wanted to avoid the obvious pyramid scheme jokes, but I wind up making them anyway. So screw it.
I like the idea too.
The worst thing that can happen is you send it out and it fails horribly, and then you wonder when was the last time it actually worked the way you thought it did.
Well, that's why you get pre and post data.
Right, right.
Because then you can always do post calculations to come back to what the drift should have been. Now, over the course of several years, I will say that most things don't drift by that much, but
right.
You do have some weird situations. And like I said before, you got a potentiometer that that's set to some particular setting, and the wiper gets knocked a little bit. That's going to keep trending towards whatever the lowest gravitational potential energy is, and that's going to keep screwing with your electrical readings in the meantime. So that's
yeah, it was just to the point that if it comes back the same, it's okay. That's kind of how it's supposed to. I mean, it's never exactly the same, but you just don't want to get into a situation where it comes back and it's horribly off, and then I don't know. But Yeah, and to some degree, a calibrated instrument's kind of like with a inherent bias, because you know it kind of drifts back into middle ground if it drifts consistently.
That's a big if.
Yeah, it's just if you have a track record. Some regulatory reasons people don't like to see that. It kind of looks like you intentionally miscalibrated it, but it kind of depends who you're talking to.
Well, the other thing is that if you're talking about a built device versus a manufactured device, if you see the difference then out there, if you're seeing something made by a community science group, for example, usually you have more control over the actual build process, and you can actually control for that error ahead of time. So that's part of the reason that we have that step 1 in the 5-part plan that we've been working on here at Cornell, is that then we design it first, and then step 5 is people come back to us and say, well, you screwed up, and here's how we redesign it.
Sure. Right. Joe, you have a question.
No. Hello. Wonderful talk. Very interesting. That's not a question, though.
No question.
Tell me more about the penguins.
I've got a meeting actually on Thursday about that out in Minnesota. There's this issue where my colleague Michelle LaRue, who's out there at UMN, has been tracking populations of penguins by looking at satellite images of their poop. Not even kidding. And so apparently she was at this this conference called Idea City up in, I think it was Montreal, last year. Ran into somebody who was very interested in the fact that we have no idea where the heck these penguins are going, and decided to get together with her to see if they could get a private foundation to provide funding to actually do this. And so what we're working on now is the possibility of a tag that can survive the Antarctic winter and still remain powered to give us SATCOM back with a GPS location of the bird. So that's pretty darn power hungry, and it's not very easy, but Michelle had told me that these penguins huddle together for warmth, and we're talking about emperor penguins, and that in the middle of a penguin huddle, it can be 72 degrees Fahrenheit and -40 outside of the huddle. And a light went off in my brain, which is that creatures are normally lossy. And
so we lost you until just now, and we were all on the edge of our seats as to how the penguins were going to broadcast.
Okay. So, Michelle told me that the penguins can huddle together for warmth. In the middle of the huddle, it's 72 degrees Fahrenheit. On the outside, it's below -40 Fahrenheit. The light went on that the penguins are thermally lossy and yet can deal with that amount of thermal loss. And that's when I hit upon the idea of putting a Peltier junction on the back of a penguin to turn the thermal loss into an actual source of power that we can use, using the thermal difference between inside and outside the penguin as a means of generating electricity.
Wow. I think you just blew Joe's mind.
A headache now.
How much power do you get?
We haven't tried it yet, so...
Depends on the size of the penguin. Are these like king penguins or little penguins?
Yeah.
I think that's just the plot of The Matrix, but for penguins.
It does seem...
Only thing is that we're not altering their reality, although they do walk around with backpacks on. The water's really real, Dave.
They're using us as batteries.
Turning a human into this.
Amazing.
I mean a penguin. Sorry.
I don't know how I know this, but when they huddle, they actually like rotate and like they take turns being on the outside.
Yep, they do, and that's when we actually get the charge. Because if they're in the middle of the hull, then that means that the thermal gradient's actually lower, and that's why we also still need to have a solar panel on the back of these things. Because during the Antarctic summer, the thermal gradient is so small that we don't actually get much in the way of power out of it. So instead,
you like an ethics committee to evaluate the impact on the penguins. I'm serious. You can't just like.
Well,
Yeah.
we're going to be testing this on several other species more locally first. And we're also going to be just testing it in the lab first, because we don't want to strap a really, really cold thing to the back of a penguin that's already cold in the Antarctic winter. We really don't want to have a chance of killing these birds that we're desperately trying to track. So we want to prove out that the mortality rate will be 0 before we tag anybody.
All right, this is really off topic, but it's interesting because I don't know.
It's tangential. There are no topics. Go ahead.
No, I'm saying this is off topic, but no, I don't know. I guess I haven't really thought a lot about bird watching, but I kind of left the penguins out of the bird watching realm. Like, now I'm wondering, like, ostriches, and does like a platypus count, or how does that work? These are like, they're like on the. It just seems birds. They're not. No, I guess not. They're like on the fringe of bird watching. It's just dinosaurs.
As a birder myself, I can tell you that bird watching is not exactly the greatest source of data. Although the guys who run eBird at the Lab of Ornithology wouldn't want me saying that.
Okay.
That's probably one of our most successful citizen or community science projects here at Cornell, but at the same time you have to put huge error bars around the data, because you have no idea what the limit of detectability is, and you're essentially, from a sensing perspective, you're moving from sensor to sensor to sensor within an array with no calibration whatsoever. Even though you're doing discrete counts of discrete species, you're assuming a level of competence on the part of the observer that may not be rational.
How about ostriches? Did you follow those? Or? I don't know. I'm just really curious now. Like, what are the birds?
Find them on eBird, but I don't know if you can necessarily. I mean, we certainly could tag them, but then again, I think thermal gradient would be next to nothing for an ostrich, except for at night.
Okay. Sorry.
I think that's a really interesting point you just made about the error bars, and I think, I mean, you know, in some ways it's
the curse of citizen science. And that's
and also the difference between community science and citizen science, right? In citizen science, you're, I mean, essentially treating the people as a sensor, and it's not a hyper-reproducible methodology. In community science, the people have sensors; they're not sensors themselves, and I think that's an important distinction. So
not sensors, but sensing systems. But yes, I agree. Sorry, I'm being pedantic. It's my nature. I have to discriminate between sensors and sensing systems because they're two discrete things that I make.
Sure.
But Jeff definitely. Jeff or Jeffrey?
Either. Jeff is shorter, though.
Okay. Jeff has an excellent point, because when you treat the human as the sensing system, actually we went through this in my class the other day. I'm teaching this environmental instrumentation class here at Cornell right now, and for my first class, I brought in a bag full of apples from the Cornell Orchard store. Yes, I am lucky to work where I do. And I passed apples out to everybody, and I went through the 5 senses, and then we went through what each of those senses actually decomposes to if you were to use an electronically based sensor instead of the sensory organ that you have in your body. And we wound up with a list of, I think it was over 36 different types of sensors that you need to have, minimum, just to mimic smell alone. And then when you start getting into tactile sensing, and you start getting into how tactile also includes temperature, but then taste also includes temperature, and there's all these Venn diagrams that you can make. Humans as sensing systems, yeah, we're very good at it. But at the same time, because of the subjective observer that's in here doing the perceiving, getting quantitative measurements out is an absolute nightmare. And you can quote me on that.
I think we're losing this room.
Yeah.
Okay. Oh, sorry. Okay, I guess we just realized that we're being kicked out of the room that we're in here, so we're gonna have to go. I wanted to talk about penguins more, but
well, you can always call me.
Yeah, right. Exactly. Yeah, we can.
Besides, Don, we're gonna have another instrumentation time, and I have this odd feeling that I think a few of these people might possibly tune in for the next one, or even participate.
Let's bring them in. Yes. Okay, great. Sorry we have to go really quickly now, but
Thank you so much.
thank you. Everybody says thank you. Oh,
Thank
God.
you very much. Thanks a lot. Good stuff.
Yes. All right.
Thanks a lot. Take care, everybody.
Take care.
Thank you.
Bye.